Okay, right. I can presumably hook this somewhere. So as I say, I came to this project a bit late, but not late enough to do a substantial amount of programming. Eventually, the program for this model was published in 2016, I believe. Yeah, so that, I mean, it turned out to be a huge programming project, and well, it involved a lot of testing as well. Anyway, I came to this. I was introduced to David by my PhD supervisor, Ron King, who's indeed listening in at the moment. And Ron spotted a similarity between the types of calculations we were doing in invariant theory with the well, aspects of the algebraic collective model. And I will touch on this later. So first, I'm going to point this out. I think I've destroyed it again. How do I make it go forward? Okay, so first I'm going to introduce the algebraic collective model. So this will be a very basic introduction for new physics-oriented people. And after that, I'm going to sort of switch into my mathematical mode then. So I'll discuss reducing representations of SO5 down to SO3 and actually producing a generating function, deriving a generating function. So I'll be doing maths here. It will turn into something like a maths seminar. So I will go through a derivation, and you might want to come closer if you can't read the details. And for this third section, it's very unlikely in the time I've got, I'm going to get to that section, but the salient points will become apparent in section 2 anyway. So, well, these are actually David's words. The algebraic collective model is an algebraically sophisticated version of the Bohr model of the atomic nucleus, in that all matrix elements of a vast range of potentials can be calculated analytically. So that's the idea. So we've got the Hamiltonian of relevance here. So it's the standard looking Hamiltonian here, and this is of course the Laplacian, and I've rewritten it here in terms of 5D spherical coordinates, and beta is a radio coordinate. Oh, sorry, wrong button. And gamma is part of the spherical coordinates. So, yeah. This lambda squared here is the second order Casimir operator for SO5. So here, as I say, beta is a radio coordinate. So it's just positive real numbers, or really non-negative real numbers. And gamma and omega are standard coordinates on the 4 sphere, S4. And gamma is in that range, and omega is an element of the rotation group in 3 dimensions. So in effect, there are 3 parameters hidden in there. So that's why this is a 4 sphere. So in the case that that potential term doesn't actually depend on gamma, so the potential is actually invariant in 5-dimensional rotations. The eigenvalues of that Hamiltonian can all be taken to be of this form. So these are the SO5 spherical harmonics, and well, the important point here is you've got a V in both terms. And that's N, that label N is just some set of labels, doesn't matter. So effectively, it's been diagonalized independently on the two different spaces, the diagonal on the radial space and on the spherical space. So as I see, these are SS5 spherical harmonics, and they satisfy these eigenfunction, eigenvalue equations. And so this is all pretty standard stuff here. Oop. So here the eigenvalue of gamma is V times V plus 3. For the angular momentum operator is L times L plus 1 normally, and for the magnetic operator it's M. So these are good quantum numbers, V, L, and M. And they're, oh, sorry, it should be L squared, yeah. Yeah, that should be gamma squared as well, yeah. So these quantum numbers are the seniority, the angular momentum, and the magnetic quantum number, respectively. And alpha is another label that we need here. And well, the standard terminology is to call it a missing label because it doesn't actually correspond to an operator. But it's needed to distinguish states with equal V and L in some cases. So we want a basis for the Hilbert space. And in fact, we use a variety of different bases. So they look like these. These are states on the radial space, the radial Hilbert space. So that this is perhaps a bit of strange notation. So nu is like the standard harmonic oscillator label. So that ranges from 0, 1, 2, etc. And here we have a couple of parameters for those harmonic oscillator states. So I'll mention those later on. And here we have the states corresponding to the SO5 spherical harmonics. And these are the ranges for all these indices. So these are all standard. And the alpha label, the missing label, ranges between 1 and some value D, which depends on V and L, depends on the seniority and the angular momentum. So we're going to actually derive these D, V, L below. So here, as I say, A and lambda V are certain parameters, and they can be adjusted in the computer code to improve the efficiency of the code. And in fact, they have a huge impact on the efficiency of the code. And well, yeah, I mean, it can make the calculations practical as opposed to impractical. So yeah, you need some way of choosing these, but I'm not going to go into that in this talk. So as I mentioned, these states correspond to the spherical harmonic wave functions, while these correspond to modified harmonic oscillator wave functions. So there's the explicit expression. So it'll look quite familiar to you, but there's a slight difference because we've got these two parameters, A and lambda, in there. So I mentioned there that this is a generalized Laguerre polynomial. And also mentioned there that when lambda minus 502 is a non-negative integer, these are standard radial wave functions for an isotropic 5D harmonic oscillator. So I'm just going to make some comment about these parameters, lambda V. Now, a lot of the potentials of interest are parity preserving. So I didn't have a time to write in what that actually means. But it turns out that these parity preserving operators are obtained analytically when this lambda satisfies this constraint, lambda v plus 1 minus lambda v is odd, for all v. And in David's initial program for this, and in fact in the default use in the program that I subsequently wrote, the user chooses lambda 0, then the program sets lambda v to be equal to lambda 0 when v is even, and lambda v to be equal to lambda 0 plus 1 when v is odd. So this is very trivially satisfied then. So that works very well. So this is where I switch from a physics voice to a maths voice. So I'm going to now talk about characters of representations of SO5 and indeed SO3 and SU5. So I don't know if people far back can see that. I mean, yes. Can you read that, Joe? Oh, you've got a laptop, okay. So here, chi superscript SO5 subscript V denotes the character of SO5 having highest weight V0. So that's a very obvious notation. So we want to find an expression for this, but we're also going to need the corresponding character of SU5. And the corresponding character is highest weight, V000 there. So in fact, what we're going to do is we're going to reduce from SU5 down to SO5. So to do that, and to find something relevant to the spherical harmonics, we're going to use generating functions. So we're going to take these characters, we're going to multiply each one by t to the power of v, and we're going to add them up. So this is a standard trick in maths, and I'm very fond of it. So almost everything I do, I try and convert it to a generating function for, and then you can do lots of calculations at once. So that's the SO5 case. We've got a corresponding generating function for the SU5 case. I should say that t here is a parameter, but it's usually regarded as a complex number with modulus less than 1. And that means that we can then add things up using geometric series and such. So in this case, these are symmetric functions corresponding to one-row partitions of degree v. So it follows that we can write down this expression. Yeah, if you think about it, every t to the power of v will then pick up v values from x1 up to x5. Then, so in all cases, you'll get a symmetric function. So that's exactly what we want for this. And here, x1 up to x5 are the eigenvalues of SU5. Now for SU5, the product of these is going to be 1, but that doesn't concern us. It comes out in the wash later on. Now, when we restrict from SU5 to SO5, then we need to specify the two independent eigenvalues of SO5, and these will be Z1 and Z2, and then the 5 eigenvalues of SO5 are then Z1, Z1 inverse, Z2, Z2 inverse, and 1. So these eigenvalues are then restricted to this case. So, well, it's well known that a a representation of SU5 decomposes in this way, just by taking out trace terms. So you have this one-row representation. You get the corresponding SO5 representation. Taking out a single trace gives you that, where the index is 2 less, because the trace takes away 2 terms or 2 boxes from the end diagram. And also you get V minus 4, and the index here decreases by 2 at each stage. So at the end of this line, you either get chi subscript 1 or chi subscript 0. So if you subtract one of these, well, from one of these, if you subtract the same one with the index 2 less, you'll just end up with the leading term of the first series. So you've got that. And we also have to define chi subscript u to be 0 whenever u is negative. So that's needed when v is 0 and 1 here. Okay, so we also have to consider the branching from SO5 down to SO3. So SO3 is the physical group which our model sits. So SO5, on this restriction, SO5 becomes the irreducible 5-dimensional representation. So it's the L equals to angular momentum representation. So if on this restriction, the eigenvalues of SO3 are Z, Z inverse and 1, all SO3 elements can have their, well, do have all their eigenvalues in that form, where Z is e to the I theta. Theta is the angular rotation. So if the eigenvalues of SO3 are those, then those of SO5 in the 5-dimensional representation are Z squared inverse, Z inverse and 1. Yep. So we're interested in seeing what happens on restriction from SO5 down to SO3. So there'll be a branching rule for the characters. And these are the multiplicities that arise. So that if you remember, these are actually the numbers for the range of the missing label on our spherical harmonics. Yep, so as I said there, this defines the branching multiplicities. So we're going to be particularly interested in these values, D, V, L. So to get access to them, we're going to make use of the well-known expression for the character of SO3 of angular momentum L. So it's that quotient, that's in effect the Weyl formula. So what happens on the next page? Okay, we also have an orthogonality relation for characters, or all the characters of Lie groups are based on orthogonality relation. And so we have the product of the character, a product of the complex conjugate of a different character multiplied by the Haar measure on the space. So that's what the Haar measure looks like for SO3. It's just simply 1 minus cos theta. So the orthogonality relation is the integral of that between 0 and 2 pi. And that is 1 when this L and this L prime are equal, 0 otherwise. So now we just convert the theta variable to Z and turn it into a contour integral. So a bit of playing around with standard trig functions gives you that. That's another standard manipulation. And so that expression now turns into this expression. So we've got the two characters again now, and the Haar measure has now become 1 minus z all squared divided by z squared dz. So that's simply a rewriting of this expression. And we're now integrating around the contour z. Modulus of z is equal to 1. So this is the way we defined these branching multiplicities. So using that orthogonality relation, we now multiply both sides by a different SO3 character and integrate. And we get this expression for these branching multiplicities. And now we write in the explicit expression for the SO3 character. That's a Weyl expression. We need the complex conjugate. And that turns it into this expression. So instead of calculating this, the subscript v of L, we're again going to calculate a generating function. So here we have two parameters, S and T, and we sum over all values of V and L greater than or equal to 0 of these dummy parameters, T to the power of V, S to the power of L times the branching multiplicity. And again, it's very useful to assume that T is a complex number of modulus less than 1, and S is similarly modulus less than 1. So, okay, so we're going to substitute this expression into here. And we're going to see if we can do some manipulations to actually calculate this generating function explicitly. So doing that substitution gives us this expression. So you see we've got the sum over V and L in here. And it's only these two terms that involve V. So that's split off there. And it's just these terms that involve L. So that's been split off there. And that, you might remember, is the generating function for one road SO5 characters. So that's how I denoted that previously. And here, in this summand, I've slightly rewritten that. This is just, well, I mean, you can almost say it, the Z squared has gone there. And we've got S to the power of L over Z to the power of L there. And S to the power of L over Z to the power of L plus 1 there. Okay, so now each of these are geometric series. And we've taken the modulus of S to be less than 1. So because Z is on this unit contour, the modulus of this quotient is less than 1. Likewise, the modulus of this is less than 1. So we can happily sum these up using a geometric series expression. So that's what I've done there. That's that expression. So you remember that the geometric series gives you this. And for this one, you've got a Z to the power of, well, Z to the power of 1 we can take out. And we've got 1 minus SZ in the denominator. So we've got the difference in these two terms, and it's convenient to just put these over a common denominator, multiply up, and that results in this expression where we have a convenient product in the numerator. Okay, so that's that expression rewritten. So I can substitute that in. This is the one we derived before. If I just go back, where did I derive it? yeah, this is a I have a feeling I've left a page out. Okay, I left a page out, so I'm going to have to wing it. I did actually write the page. You remember when we reduced from SU5 down to SO5, we had to take this x1, x2, x3, x4, x5 to be first z1, z1 squared, z2, z2 squared, and 1. But then we reduce down to SO3, and we have z1, z1 squared. No, sorry, they don't have subscripts anymore. We have z squared, 1 over z squared, and 1. So that's what happens there, and that's for SU5. But because of this relation, we have the difference between two such expressions. And it would be so much easier to see it actually on the screen. But this means that you end up with a 1 minus t squared in the numerator, that t squared corresponding to the v decreasing by 2 at each stage. And it cancels with a 1 minus t, or it partially cancels with a 1 minus t in the denominator. So you end up with 1 plus t in the numerator and a product of 4 terms in the denominator. So I doubt if you could have followed that, but but the result is, as I just said, we can substitute now that expression I've just talked about there. So that gives us the 1 plus t up there and the first 4 terms in the denominator there. And we also have a 1 plus s in the numerator. And we have a 1 minus z squared in the numerator. And we have a z minus s and a 1 minus sz in the denominator. So that's the result of that manipulation. So of course, what we're going to do now is we're going to use the calculus of residues to calculate this contour integral. And the first thing to do is, because it's hard to see what's going on with these two terms, is to multiply them up. So this one turns into z squared minus t, and we need to multiply the numerator by z squared as well. And this one turns into z minus t, and we need to multiply the numerator by z. So that's reflected there. So now we can see, well, let's see what the slide says. So now we use the fact that the moduli of s and t are less than or equal to 1. And we can see that inside the unit circle, inside this contour, there are poles at z equal to s, z equals to t, and z is equal to plus or minus t. So taking residues of these poles then gives, after a bit of algebraic work, this very, very nice expression. So this is the generating function I wanted to derive for this, for these branching multiplicities, dVL. And this tells us the ranges of the missing variable. All of them in one expression, albeit slightly hidden because it's a generating function. So it does actually allow us to give an explicit expression for this multiplicity. And well, I mean, this is well known in literature and in our papers as well. And I didn't have time to write it down explicitly, but that wasn't really the point of what I was trying to do. The point is that this expression suggests a way of building up the spherical harmonics. So these terms have seniority 3. Well, this term has seniority 3 and angular momentum 0. This one has seniority 1, being the exponent of t, angular momentum 2, this one of s. This one has seniority 2 and angular momentum 2. So when you expand these out as geometric series again, you'll have arbitrary amounts coming from this one, arbitrary amounts coming from this one, arbitrary amounts coming from this one, and just one possibility coming from this one. So this is a typo, that should be a plus. So this suggests that to get any spherical harmonic, we can start with just these 4 cases and somehow multiply them together to get any spherical harmonic. So that's the idea. And well, David had already done this. So this is, as Mark was saying earlier, David had already done everything you've done. So, but this is what I had to do to convince myself that it was right. But David already knew this. So this is the idea. We build up all spherical harmonics from these 4 cases, having these what I've called bidegrees here, and choosing m equals L for the magnetic quantum number is most convenient, because then we just have to deal with the highest weight components. And this fixes the 4 spherical harmonics to be these cases. And these cases are already well known. They can be expressed in terms of, well, in that case of that one, Legendre polynomials, and for the other one, the Wigner-D functions. So they're well known, and you can multiply them together according to that generating function. You build up all spherical harmonics. You have to use a Gram-Schmidt orthogonalization process, but you get them all, and then you can calculate the Clebsch-Gordan coefficients. And well, that's what we need to carry out the calculations in the model. So I don't know how close I am to finishing, but I suspect very close. Yeah, I mean, as I've derived things, it's only a suggestion at this point, and you can make things more concrete by considering SO3 invariance generating, but by the angular momentum 1 and 2 representations. So yeah, so really that's probably a good point to stop. Okay, thank you for your attention.